Hello, everybody. Good morning. This is Bogdan. It is my second time here at the Linux Loon conference. First time as a speaker. I'm a bit nervous. Hope it will go well. So today I will give a talk about the Intel processor trace. It is a hardware piece of functionality that allows users to debug and troubleshoot performance issues non-intrusively. So a bit of myself. I have a PhD in real-time systems from Linköping University. Currently, I'm employed by Wind River, not Wind Driver. And yeah, of course, my hobbies are Linux compilers and performance-related tools. So despite the fact that my employer is Wind River, this is a talk about Intel, and it is not affiliated with Wind River in any way. So, yeah. What is the Intel processor trace? As I said, it is a piece of hardware that allows for capturing information about the software execution with minimal performance perturbation of the software being traced. And it generates lots of packets. One has to read the manual to see how that piece of information looks like. But all the packets that are being generated, when combined with the binary, with the actual binary being traced, will allow the users to reproduce the execution trace, to reveal timing information, and the flow, how the software executed, and can allow for advanced debugging when it comes to tiny, gritty details that may affect the performance of the execution. The Intel processor trace is designed to work with the so-called PEBs, the processor event-based sampling. And I will say what that is. So, you have the traditional PMU subsystem, the hardware subsystem, where you configure PMU events and you wait for them to happen, and the counter, the particular counter is incremented. So that is traditional way of doing performance investigations. And now you have the so-called PEBs, where besides the actual events being counted, you can even record extra information, like the instruction pointer, and maybe some other registers. And for some particular events, you can even record the memory address that triggered the increment of that counter. But of course, one has to check the manual of the CPU to see exactly which events are available and how can they be used. The main thing with the PEBs is that it provides more information than the actual, than the traditional way of doing performance investigations. So it is, you have the actual event and then the CPU state, whatever CPU state means. So again, you have to check the manual. Now, when it comes to the processor tracer, so what I like the most, it is this new instruction that Intel has. It is the picture write instruction, which allows for users to complement the code. So you put the picture write instructions in different places in your code. And then this instruction will output the packets to the Intel processor trace, which can be taken offline, so to say, and you can reconstruct the execution flow, where you can check for performance bottlenecks. Yeah. Is it okay? Yeah. So. The picture write instruction works against let's say, the traditional registers like the AX register or BX register. So first you have to load into those registers your payload. It can be a marker or it can be a variable. You have to load it into that registers, and after that you do picture write AX, and then that piece of information will go to, it will be logged by the Intel processor trace. So if you want to use it in your application or in your system, how can you do it? First of all, given that you have an Intel processor, you have to check with CPU ID what are the exact capabilities. And after you detect all these capabilities, you have to write to some MSR registers, how to use it, and it will be working. However, if you have a Linux system, you can just do it via the perf event OpenSyscall. It is very easily. And you have to go to the manual of these syscalls. You have to see what data structures you have to populate. Maybe the most important data structure, it is this one, perf event attributes, where you have many fields, but the two of them are very important. The config field, which says that you want to use the Intel PT hardware. And then, the type, you have to take it from the sys file system to see what type you have to give to the syscall in order to detect more Intel PT functionality in the kernel. You get the file descriptor back, and then you do an mmap towards that file descriptor in order to give memory to the Intel PT hardware so that all these packets that the Intel PT outputs will be placed in that buffer of memory. Of course, you have to do a bit of mmap tricks, as the manual says. And in that memory, you will have the so-called auxiliary records coming from the kernel, and you have to decode those records, and there you have the Intel PT packets. In order to decode those records, you really have to go to this chapter in the SDM, Software Developer Manual, read exactly what it does and how these packets look like, and then you will be able to decode that piece of information. So this now it starts to be funny because this is the first thing you have to do when you are working with the Intel PT hardware. You have to be really fast in decoding that piece of information because the kernel or even the hardware will detect that you are not fast enough, and then it will put the perf system on hang, and you may lose information. So what are the use cases for the processor tracer? As I said, timing investigations. You can do instruction tracing in two ways. I will show how. And you can correlate with the PMU subsystem in order to check for other events like, memory loads, cache events, and so on. And you can reconstruct the execution flow offline out of the traces that you get. So when you have this, when you use the Intel PT hardware, you have to have a consumer and a decoder of those packets, and all these use cases that I will present today require that you have this decoder. And of course, the decoder running on the system needs to have some resources allocated to it, like CPU and maybe memory. So in my use cases, I do it like this. You have the traced CPU running a piece of software that makes use of the entire memory subsystem. And that core, for example, has the Intel PT hardware activated and configured to trace the piece of software that you are interested in. And on another core, some are separately, maybe with some sort of isolation, you have the decoder getting packets from the Intel PT hardware of the particular core being traced. And those packets are being decoded, and after that, they are written back to maybe main memory or disk for offline, for more offline investigation. So already now in this picture, we can see if the cache memory or the memory subsystem is somehow shared. Probably there will be some interference between the decoder and your workload. Hopefully, with all the isolation tricks that the hardware allows you to do, that interference is minimal. So the first use case for the Intel PT hardware is to do time measurements of your software. So on Intel processors, the traditional way of doing this is to read the timestamp counter, which has a bit of overhead. You instrument your work with read before and read after, and you record the difference. Another way is to use the PT write instruction, where, as I said, you have to put in the AX register your marker, a marker for starting the workload and a marker for that, which suggests that your workload ended. And then again, you offline now, you can record the time difference between start and end. Now, what is the difference? As I said, PT-Write allows for non-intrusive instrumentation. So if these markers are constants and compile time constants, then the overhead for putting something in the AX register will be minimal. And the PT-Write has a 1 clock cycle overhead according to the manual. So doing instrumentation in this way, it is less intrusive than the traditional way of where you have to read a timestamp counter. So yeah, low overhead instrumentation, which is very suitable for small pieces of code where that noise from the timestamp counter can be too much. And you have to keep in mind that both instructions are not serializable, which means that if you really want to avoid out-of-order execution interference, then you have to maybe put some memory fences. So this is again something which you have to investigate on your own and decide if you really need those fences, because again the fences will impact the timing of your software. But this is something which one needs to keep in mind. So both instructions are not serializable. Again, so when it comes to time measurements, the good thing with the processor tracer is that each piece of hardware, which is per core, so to say, has its own cycle counter, which runs outside from the TSC. Yeah? So the TSC is synchronized among all cores, and this is one of the reasons why the read TSC instruction has a larger overhead. But the cycle counter, it is per core, and it is not synchronized in any way with the other timing infrastructure that the processor has. So this is one of the reasons why using the PT hardware together with the cycle counter gives more accurate timing. And of course, yeah, from time to time, the processor tracer outputs the exact TSC when it feels like the wall time, it is hard to be reconstructed offline. Again, you have to read the manual to see exactly what that means, but the processor tracer is aware of that, and from time to time you get the TSC as you have done a read TSC instruction. The main thing to keep in mind here is that this cycle counter and the TSC may not operate in the same frequency, and you have to do a transformation when you do the off-life analysis. Another use case for the processor tracer is to correlate the software execution with the so-called PEBs, as I said. So again, you have to use CPU ID to see if PEBs are supported to output packets to the processor tracer. And maybe you have to use these links or the SDM, the software developer manual, to see exactly how it can be done. But let's say we go for these links, and then there you check the PMU events. Let's say we are focusing at this branch instruction retired event. And then you will see that this event is PEBs enabled, and it can be mapped to any of the available PMU counters. So in the particular case of this CPU, which I am showing, there are 6 general PMU counters. And this one can be mapped to any of these available 6. So you do perf event open, you configure the event, and then the kernel subsystem will choose the next free counter. In case all of them are being used, multiplexing will take place, and you don't really know which counter you will get back. You have to do the mmap to see the index of the counter which you are using. But anyway, let's say that you got a counter and you map this event into a PMU counter. Then, given that you have PEBs capability to Intel PT, every time when this event is triggered by the software execution, which means that you have branch instructions being retired, you will get packets into the processor tracer. So. As I said, so you will probably, some of these events are of interest, like instruction retired, branch instructions retired, and mispredicted. You do perf event open for any of those events, and then the Intel processor hardware will put that piece of information into your memory buffer, encoded as these packets, BBP, BIP, and BEP, which means block begin packet, block item packet, and block end packet. So if you go to the manual, you will see what is the definition of these packets and how they work together with the PEPs functionality. For example, if you have this type 04, you will see that it is a PEPs enable event. And then the BIP, the block item packet, will have the payload of that event. So as I said in the beginning, PEPs allows to record more than the actual event. So it is the instruction pointer, a timestamp, and the applicable counter. So this is what the CPU state means when in the context of PEPs. And that this CPU state is outputted to the processor tracer, which allows for non-intrusive and offline investigation afterwards. Now, the hardware has even the PDIST functionality, which is precise distribution. So if we go back to this event branch instructions, for example, as I said before, it can be mapped to any of the 6 available counters, but only one of these 6 counters, it is PDIST enabled. Unfortunately, even the modern Intel processors do not have more than 1 or 2 PDIST counters, so you can't do that much, but this is what we have. So when you configure some of these events, and given that they are PDIST enabled, you will be sure that when the event is encountered, then it is exactly when the instruction was retired. There will be no skid into when the hardware reports the event as being incremented. Right. And one of the things with perf event open is that you can't really say, I want a PDIST counter. There is no way of saying that. You just have to trust that the perf subsystem, it chooses the first counter. So there is no flags, nothing to say to the syscall that I want a PDIST counter. Right. So just to conclude a bit here, it is a hardware feature so that PEPs are generated exactly when the instruction has retired. Now, there are some limitations, of course. It is not that beautiful, so only selected PMU events are PDIST enabled. And according to the documentation from Intel, it works well at a distance of 256 retired instructions. So you can't have four consecutive instructions. I don't know what are the limitations behind that, but this is what the manual says. And even the kernel or the perf subsystem doesn't allow you to put a reload value for the counter smaller than this one. Right, now I am going to show you a small demo for the next use case. Okay, let's see if it will go well. So, okay, so this is how I will just show this slide. So this is, for example, how the processor tracer outputs packets. So you will have lots of information, but I'm not sure if, does the mouse work on the screen? Yes, it works. So when the hardware records the execution flow, it will output, as I said, many packets, but some of them are very important, like this, where is the mouse? Like this tip, the target instruction pointer. We start the execution from this address, for example. And then we have the so-called TNT packets, which are taken, not taken branches. And then based off this information, together with XED, which is the instruction decoder, you can actually decode offline, how the execution flow went. So I have a test program in this case, and I can say it was the instruction at this virtual memory address, which in the object dump has this address, and then it was a move, it was a shift, it was an OR, and so on. So let me show how it works to see if I can make it here on this big screen. Right. So if we go to, so this is the test program. It is not very advanced. It is just doing a busy loop and some if-else, a call via a pointer to function in order to have indirect branches, and then some free and malloc, nothing advanced. So this is the object dump of this test file, and let's go to 13D2. Yeah. So this is the object dump, as I said, and the processor tracer tells you 13D2, D5, D8, and so on. And you can correlate directly with object dump output, where you see there is a move, and this is the bytecode of that instruction. There is another move, a shift, and so on. And this is the sequential execution as the processor tracer shows here in this picture. Move, move, shift, and so on. And you can have here, you have here move, move, shift, and whatever comes after. Now, this is just sequential execution. You will say it is easy. What happens if we have branches? Yes. So now, if we have branches, and let's say we start from 1481. Let me go there. Right. So you see here the processor tracer. 1481, it is here. The processor tracer says there is a move, and then I will do a call, and then I will do something else, and after that, from my test program, I will go into libc, and I will do other stuff. So let's see how if we go back to the object dump, which is here, so at 1381, we have a move, and then I have a call to malloc, for example. And this is done via the PLT because libc it is linked dynamically. So this call, it is in fact a direct call. Yeah, it just jumps here at this address. No indirect jump. It is a very easy jump. Okay. This I have to go back. Right. So this is the PLT entry for the malloc call. It just jumps here. And you see even in the execution that from 14-something, I jump to 1160, which is the PLT entry. And the actual call to malloc, which is an indirect jump, is done through the instruction pointer with an offset. I have to read from memory, to read this register at the offset. And the content of that memory address is the address where I jump. So at 1164, I will do the actual call. And after 1164, the tracer doesn't really know what happens. It will wait for the for this call to retire, so to say, and it will give me another packet which is called tip, the target instruction pointer, and it will tell me I have jumped there. So at 650 in the virtual memory space. And yeah, from 1164, I will jump here into libc, and let's see what is at AD650. At AD650 is the actual malloc. Yeah, so one can trace offline whatever happened in the software being traced. And it works like that. So from libc, I will go back when I will see the return. I will go back into my program or whatever the flow tells me I have done. Now I'll go back to my presentation, which is awesome. So now this, so we are here. I have presented this stuff, how we can even correlate the execution flow with jump instructions and indirect calls. So as I said before, you can even record the CPU state. The processor tracer will tell you even more. So at that instruction, the conditional branch JZ from libc, given that I have configured the PMU subsystem to record some cache events like, let's see what happens if I have L1 hits or L2 misses and so on. So for that particular instruction, the processor tracer recorded that I had a L1 miss, which in fact was a L2 hit, and it is correlating these two events with the instruction. Where is this mouse? Which is this one. Yeah. with the instruction from this address. So even more, you take this, this information with the events being, or with the CPU state being reported by the Intel processor tracer, you put back this information into some cache simulators, and you can see how you can optimize both hardware and software for future use cases. So instruction tracing can be done like this and can be done in another way. So for example, you need, if you have a modified kernel where you put the execution or the processor in single step execution, with maybe in this way. So if you have the execution in single step, you can do more. It will be slow, but you can do even more. You can correlate the software execution with kernel state. Yeah, whatever objects in the kernel are important for you. So the fact that modifying the kernel and running at single step, it is slow. Of course, the timing is not as accurate as the previous use case, but maybe the advantages are that you can do a bit more and you can correlate with extra information that you will never get from the hardware. So conclusion on this one is that you can do instruction traces in this way with advantages and disadvantages for both sides. Maybe for the one you need a modified kernel, you have to modify a bit the software to handle timeouts because it will be a slow execution. But for the other side is that you will have lots of data being generated by the PT hardware. I'm not sure if you have enough memory to do it or if you are fast enough to decode it. So there are other advantages and disadvantages for both sides, and hopefully they can be combined offline in order to correlate or to make use of advantages from both sides, so to say. And there are even more advanced use cases which I am working on. So stack unwinding, for example. So if you are doing instruction tracing in kernel in single step execution, you have access to everything. You have access to the stack. So from time to time you can do stack unwinding to see how the stack looks like. And with help of picture write, you can output the stack pointers, and it is so much faster than lib unwind. And you can even do compile time instrumentation, so you can write a GCC plugin. This is under development. You can have this plugin so that maybe with help of Pragmas or whatever, you can complement your code so that your compiler knows that here maybe I have to put some picture write instructions for begin and end so that I can instrument that piece of code and then place it back into the compiler with help of the already existing PGO, profiler guided optimization infrastructure. Yeah, of course, I already spoke about it, so you have to give some resources to the PT hardware. It is up to you to decide how you do that and what level of isolation you can achieve. But this is always something to keep in mind. And then, while doing this, I found some bugs in the kernel. Maybe you know this guy, Alexander Shishkin. I have reported these things to him. And he will take care of the bugs being fixed. And I want to end with my vision over the PerfSoft system. Maybe you will not agree with it, but I have to throw it up here. I think the PerfSoft system needs to be moved in the user space. It is not its place in the kernel, given that the traditional use case, it is just to investigate performance bottlenecks. You don't need it in production. I don't see why it has to be in kernel space. I think it can be a full user space toolkit in the future, something like DPDK or similar, and I hope it will happen. Thank you. Questions? Yeah, so this is a very good question. If if the process migrates, then you will not get information as it is today, because the perf event syscall, you need to give the PID. So if the PID is not anymore on that CPU, it will not generate packets. Yes.
You said that you wanted to move it, like in the future, you wanted to move it to user space.
Yeah.
I think what we've seen from DPDK and SPDK over the years is like, I mean, it's good to give like a push to the kernel people to make them do better. But it's kind of like on the storage side, we've seen that, yes, SPDK and DPDK was good at kind of showing off, hey, you could do things. But in the recent years with IOU ring, we kind of seen like, well, you really, I mean, SPDK is great. You have a user space stack, but really you want to have the Linux tools, like the kernel tools, perf, all those things that are need to like instrument the kernel and so on, your I/O path. So what specifically are you like user space? What is there something here which makes it a really good case for user space? Or is it something where I can do better than all of you kernel guys? And then 10 years down the road, it's like, well, kernel guys is back. What's up? Got anything?
Yeah, I mean, probably right now it is this feeling that we can do better than the kernel guys. But I think it will allow for faster development and faster or better ecosystem, because even ARM has similar stuff. It is called CoreSite, so I think it will be better to have unified framework when it comes to this stuff. I think it will be easier. This is the main reason behind better unification.
I think for CoreSite specifically and like those embedded system things, there is like some implied paradigm here that you are doing this analysis on the device under test. And I think with the CoreSite and this Intel Trace hub thing that is not mentioned here, there's actually possible to use what they call a combi probe, I think, and just like investigate the system from the outside a little bit like,
Lauterbach or?
Yeah, it's called an in-circuit emulator, I think, the academic term, that you more remove the monitoring from the system so you don't disturb the system. Have you looked into that or seen any of it?
The thing, when it comes, just to comment a bit on the first part with CoreSite. So when it comes to CoreSite, the difficult part is to get ARM-based computers which have the CoreSite enabled on the motherboard. I mean, to buy them from Dustin or whatever. ARM has this, they choose to burn it out or to fuse it out, so you can't really, I mean, you buy an Intel processor, you have it there, you just do some MSR writes and you can enable the processor tracer. But for CoreSite, it is not possible, me as an end user. I have to go to ARM and ask him, can you give me a computer which has this enabled, not fused out on the motherboard and so on. It will never output packets to memory. So it is difficult for hobbyists to work with CoreSite. It is maybe easier for companies like, you know, which are doing business with ARM. But I'm not sure how the developers there, how much they are interested into that, because they have other work to do in the end. I mean, they are not in the business of exploring CoreSite. So I don't know. I mean, it is on that line of thinking mostly.
Yeah, I think that I don't think it's ARM that says we're disabling it. It's every chip manufacturer that says, yeah, this is very good. We want to have it. We have it ourselves. But we don't want the customers to have it. Because then you can break security completely.
For example,
so,
yeah.
So,
yeah.
More questions?
Linus, you beat me up to a question about Trace Hub, but I have now another question about security. Indeed, how it's enabling or enabled Intel processor tracing affects security?
Yeah, I mean, some of these things here have to be, you have to use root privileges to, I mean, at least to do the perf event syscall. I'm not sure if all the cap things you need to have. But if you want to read, if you want to go, I think I think you need to do it with root. And if you want to profile kernel code, then there is a piece of information in the SDM which says that writes to the CR3 register, which is for the page table, you know, to move page, those have to be done carefully because you expose information to the outside world. So when you have writes to the CR3 register, which means in principle context switches, then you expose which is the next process, or I mean the page table of that next process. So it is a security hole in the end. But as I said, I mean the use case, as I see, the use case for this one is maybe 90% of the cases are for performance troubleshooting in a controlled environment, where maybe security is not really an issue. Because when you deploy your software, you want to run with the highest performance, and then you'll not need to look with perf or Intel processor tracer at it, and when it is on drift, so to say. So yeah, if you have it there in the kernel and you enable it, it may pose security problems. But you can disable it.
There should be like side channel timing attacks and stuff like that.
Yeah, I was thinking to mention that, but I'm not a really expert, so I don't understand how those things work. But probably someone who is smart enough will take advantage.
More questions, anyone?
Okay, thank you.
Thank you.